Conventional software development is built on forms, database queries, and event-driven logic. This architecture relies on a linear execution model. The system sits idle, waits for user input, then responds to that specific request. That model breaks down when rendering continuous three-dimensional spaces, which demand constant frame-by-frame updates regardless of user action. Traditional computing hardware was built for static, event-driven office tasks and 2D web interfaces, not continuous spatial simulation. A CPU-heavy setup handling isolated events cannot execute the continuous rendering required for complex interactive simulations. There is a widespread assumption that real-time 3D engines, particularly Unity, exist exclusively to produce video games. In practice, Unity functions as a real-time abstraction bridge between standard logic and hardware calculation. It allows developers who write familiar code to orchestrate highly complex GPU-accelerated environments without needing low-level graphic expertise. This capability translates directly into enterprise applications powering digital twins, immersive data visualizations, and interactive training spaces. It gives ordinary programmers the leverage to control massively parallel GPU simulations without ever writing the complex rendering code themselves. Consider the underlying system required just to make a single 3D object move and react on a screen. Without an engine, a developer must manually write an entire rendering pipeline just to draw this raw geometry. They must also build a custom physics system from scratch to calculate gravity, mass, and collision detection. Third, they must also construct a scene graph. A scene graph is a specialized data structure that tracks the exact spatial relationship of every object in an environment. Finally, they have to code a continuous input loop, allowing a user to interact with the shape without halting the rendering cycle. Manually constructing all these foundational systems is an unscalable barrier for educators, medical professionals, and engineers whose focus is the application, not the engine. If professionals had to rebuild the math for physics and rendering for every project, advanced simulation would remain locked behind specialized low-level engineering. A game engine is exactly this required framework. It is a digital construction platform where static assets are injected with interactive behavior. The engine's core function is to automatically manage the continuous frame-by-frame update loop. It pre-packages the heavy mathematical operations for physics and lighting into modular subsystems that run constantly in the background. Into this framework, developers feed standard conventional programming logic via C# scripts. The engine instantly translates that basic logic command into fully realized physics-driven rendering outputs. Because this abstraction layer exists, the programmer only has to define the unique rules of the application, not the universal mathematics of light or gravity. The engine acts as a real-time automated translator, converting simple if-then code into continuous 3D reality. Achieving physical realism requires immense parallel processing power. Central processing units cannot handle this volume of simultaneous calculations alone. The modern graphical processing unit, or the GPU, is the essential hardware engine driving these continuous real-time calculations. Unity connects to this power through its high-definition render pipeline, or HDRP, which branches into standard graphics and compute shaders. Compute shaders are programs that run on the GPU outside the normal rendering pipeline to perform parallel mathematical calculations. Unity continuously updates HDRP to absorb new hardware capabilities, integrating ray tracing for accurate light simulation and DLSS. DLSS stands for Deep Learning Super Sampling, an AI-assisted rendering technique that improves performance and image quality. The developer simply toggles these features within the engine interface rather than writing the complex algorithms required to execute them directly on the silicon. Unity stays industrially relevant by packaging these evolving hardware advancements into accessible workflows. There is a common point of confusion in the industry: the assumption that using an engine like Unity means developers no longer need raw GPU computing platforms like CUDA. CUDA is NVIDIA's proprietary low-level ecosystem built specifically for general-purpose direct hardware calculation. They serve distinct use cases. Specialized scientific workloads require CUDA's low-level access to the hardware, while real-time interactive design requires Unity's high-level scene management. Standard Unity scripting does not automatically compile into raw CUDA code. They operate on different abstraction layers. Unity provides a structural environment, so developers do not have to reinvent the GPU wheel for every simulation. This software architecture dictates the daily production pipeline used by cross-disciplinary teams. The pipeline begins in digital content creation tools like Blender, where the static 3D meshes, wireframes, and environments are sculpted. This step is purely spatial representation. It creates the visual shell of a digital twin or architectural environment without any underlying behavior. These static assets are then imported into Unity. The engine acts as a central nervous system, injecting the models with logics, physics, and interaction capabilities. Sculpting static content first, then integrating it into the engine environment is the universal standard for building explorable digital worlds. In the modern landscape, static manuals and two-dimensional explanations of complex systems are no longer adequate. Healthcare educators utilize this real-time pipeline to create safe, repeatable procedural training that relies heavily on three-dimensional spatial understanding. Defense and engineering sector rely on the exact same underlying engine architecture for operational rehearsal and machine simulation. The demand for these interactive digital twins and virtual labs now spans across all modern technical and academic disciplines. Unity provides the high-level abstraction tools necessary for an entire generation of interdisciplinary professionals to build the real-time systems that define modern technical infrastructure.